So far we didn't really run the program, we only executed 3 instructions. So let's iterate a bit. Let's move through the code. At this point, we should pay attention to the different kinds of steps. We have the step into and also step over. For instructions like load S and increase, it doesn't really matter which one we pick. However, there are some instructions here in which we should be more careful. For example, this call instruction. When we get to this call instruction, we have to make sure that we pick the right step, the step that we want. If we want to further investigate what happens inside this function, which is print EAX, then we probably should step into. However, if we don't really care about it at the moment, then we should use step over. Currently, I don't care how EAX is printed to the console, mostly because this is not part of my code. I wrote this code. Therefore, I'm going to use step over. As we can see, we just executed the print EAX function. And so a number was printed to the console. It was the number 2. The next instruction, stos, is about to store a number, a dword, to this location. We execute this instruction, it doesn't matter which step we pick, and we get that the number 2 was stored to the first dword of destination list. Now we got to the loop instruction, and this is another instruction in which we have to choose whether we want to step into or step over. If we use step over at this point, the debugger is going to execute this loop until it ends, and then it will get us to the first instruction after the end of the loop, which is push 0. At this point, I want to continue iterate inside this loop. Therefore, I'm going to choose step into and not step over. If you are not really sure about what each of those does at this point, you could just later open this program and experiment yourself. Let's pick step into, and I move on to the next iteration. And another iteration. As we can see, currently 2 numbers were printed to the console, and also 2 numbers were copied. Note that 1 is turned into 2, and also 5 turned into 6. Let's talk about changing registers. If we wanted, at this point, we could change the value of EAX. Let's first find out what is the value of EAX. It is 8, which means that very soon the number 9 will be printed to the console, and also written here instead of this dword. In order to change the value of EAX, we again use the R command, but this time with a bit of a different syntax. We write REAX equals and then the new value that we want. In this example, I'm going to change the value of EAX into 100. And by the way, this 100 is in base 16. I press the return key. Now EAX has a different value. It is of value 100. Let's check it to make sure. REAX gives us the value 100. Next, we are going to execute the inc EAX instruction. And now we print to the console using print EAX. As we can see, the value 101 was printed to the console, as expected. Next, we store to memory using the stosd instruction. And indeed, we got that 101 was stored to this DWORD in memory. Let's iterate a bit. At this point, we got again to the print EAX function, which means that EAX is about to be printed to the console. Let's check out the current value of EAX. It is 3. Let's try something different. Let's try to skip this instruction. Currently, we are about to execute this call instruction. What if we could instead to move into the next instruction, which is stosd, without executing this instruction? If we wanted, we could do it. We could do it by changing the value of EIP. The current value of EIP is this address, 403.011. Just as we can see here. EIP is just like any register, and we can change it. Our EIP equals this new address, which is the address of the next instruction. Note that the change is not evident inside the disassembly window. However, if we check the value of EIP, we can see that it has changed, which means that currently the next instruction is going to be this instruction, and the call instruction will not be executed. Let's step and see what happens. We can see that we moved immediately to the loop instruction, which means that the call instruction was not executed, and we were previously at the stosd instruction. We can also see that no new number was printed to the console. That is because we skipped this instruction, and we didn't call print EAX. Let's iterate a bit more. We are again at the inc EAX instruction. We could go further with things that we can change. Maybe, for example, we can change the code. The current value of EAX is F. What if we want F to be copied to the next location instead of 10 as expected? Usually the program reads a DWORD from the source list, then it increases that DWORD, and finally it prints it and stores it to memory inside dest list. What if we wanted to just copy the DWORD without the increasing part? We could do it if we wanted, just by changing this instruction into something else. Note that this instruction is of size exactly 1 byte. It is encoded as 40. We cannot just delete instructions. That is because other parts of the program depend on the location of some other instructions. If we move all the bytes 1 byte earlier, the program will not work as expected. Therefore, instead of deleting a byte, we are going to replace it with something else. We are going to use a special instruction called NOP, or no operation. It has the encoding of exactly 1 byte, which is 90. And this instruction really doesn't do anything. It just takes space in memory. In order to replace this instruction with the NOP instruction, we can use the A command, which stands for assemble. This command is just like a mini assembler inside WinDBG. It allows us to assemble instructions, textual instructions, into the numeric representation. Basically, it just writes memory, but it writes memory in a smart way. We give it textual instructions, and it converts them to numbers, and then writes those numbers in memory. We have to specify an address which we want to overwrite. We could, for example, just copy this address. Instead, we could use EIP, because EIP currently points to this location. I press the return key. At this point, the A command expects input. It expects instructions. It is like an online assembler. It assembles as we go. I write down the NOP instruction, followed by a return key. It seems like the A command still waits for input. To signal the A command that I don't want to put in any more instructions, I just have to press the return key again. Note that the instruction has changed into NOP, and its encoding is 90. In the usual operation of the program, we expect that this D word F will be first increased and then be copied as the D word 10. We also expect to have 10 printed to the console. However, we removed the increase EAX instruction and changed it into NOP, which means that now we expect to have F copied to memory and also F printed to the console. Let's see what happens with step. As expected, F was printed to the console and also F was written to memory. Some notes about the A command. The A command is very useful by itself. It is some kind of mini assembler inside WinDBG, and it could be really useful sometimes to check things fast. Instead of using an assembler and then opening your file inside the hex editor, you could just open some random file on your computer with WinDBG and then use the A command to assemble a few instructions. Then you can use the U command, for example, to view the instructions, to view the resulting instructions. We continue iterate a bit. And next we are going to see an example of changing the memory. At this point, we are about to read a D word from location ESI in memory into EAX. If you wonder what is inside that location, we can check it right now. Currently the value of ESI is this number. If we want to view the D words at this location, we can just use the DD command over ESI. And we can see that the current D word at this location is D. This is what is about to be read into EAX. Maybe we could change this value before it is being read. This could be done using the E command. The E command, just like the D command, is really a family of commands. We can use EB if we want to write bytes into memory, or EW to write words, or maybe ED to write D words. If you were wondering, E stands for enter. In this case, we are going to use ED because we want to write a D word. We have to supply the address in which we want to write, which is ESI at this point, and also a number. We can pick any D word that we want. Let's try 17, for example. Note that currently the D word in this location is D, and it can be seen here. Whenever I press the return key, this D word is changed into 17. I could change it again if I wanted, maybe to 18. Let's continue the program and see if our change has taken effect. We first step over. Let's see what is the current value of EAX. We can see that indeed EAX has gotten the value 17. Next we have the NOP instruction, which still applies, by the way. We changed it and it is going to stay NOP until this program is ended. As expected, the value 17 was printed to the console, and also the value 17 was written at this location, inside destination list. Let's wrap up and summarize this lesson. It was mostly about reading and changing the state of the target program at the point where it is paused. Basically, most of the interesting things that we can do with the program are exactly at the point where the program is paused. We have seen a few different commands. Let's begin with registers. We've seen the R command, and in fact we have seen two forms of this command. The first one is the simple form, just R, which gives us all the contents of the registers. We've also seen the format REAX, for example, which shows us the value of only one register. We've also seen DB, DW, and DD, which allow us to display data. We've also seen EB, EW, and ED, which allow us to write data, or maybe enter data, if it is easier to remember. LM is a command which allows us to show a memory map. The U command allows us to disassemble a part of data, a chunk of data, and see this part as instructions. And we have also seen the A command, which allows us to assemble a few instructions and write their encodings to memory.